Hello, everyone. My name is He. I'm very honored to present our work, COLI, a column-based learned storage for blockchain systems. So this is a joint work of Hong Kong Baptist University and Hong Kong Polytechnic University. So several years ago, blockchain technology has attracted tremendous attention due to the great success of the cryptocurrencies like the Bitcoin. More recently, with the development of the smart contracts, which provide the secure computing and the storage services, blockchain technology has emerged as a cornerstone of many decentralized applications in a wide range of domains, such as finance, healthcare, supply chain, etc. Blockchain is a distributed ledger built upon a set of transactions agreed upon by mutually untrusted nodes. It ensures the data integrity by using the hash chain technique and the hash tree structure for each block. Meanwhile, it can also support the provenance queries, which mean to search the historical data. So despite of its advantages, blockchain systems currently suffer from very high storage costs. All of the blockchain nodes are required to store and maintain the complete blockchain transactions and the ledger states. For instance, the Ethereum platform requires about 16 terabytes of storage as of January 2024, with an annual growth of around 4 terabytes. So to tackle this storage issue, we investigate Ethereum's index, Merkle Patricia Trie, also in short MPT, to identify the storage bottleneck. So MPT is a compressed prefix tree to index the blockchain data. It has several types of node. The extension node stores a slice of a search key and a child node. The branch node branches out to a fixed number of the child node. The leaf node stores the remaining search key and its corresponding value. So in this example, we can see that MPT indexes 3 addresses with their values. So to search this address, A11, E67, we can easily follow the tree nodes N1, N2, and N4 to finally get the value V3. So to ensure the data integrity, MPT combines the tree structure with the Merkle hash tree. Each of the node is extended with a hash value. So for a leaf node, the hash is computed using its content. For an internal node, the hash is computed using its content as well as its child node's hash value. So for instance, the hash of the node N4 is computed using the E67 and its value V3. And the hash of N1 is computed using A1 and its child hash HN2. Owing to the collision resistance of the hash function and the hierarchical structure, the root hash ensures the integrity of the indexed data. So to support the provenance queries, MPT adopts the strategy of duplicating the nodes in the update path. So in this example, in block I+1, updating the address A11E67 with the updated value V3 prime introduces the new nodes N1 prime, N2 prime, and N4 prime, while the corresponding old nodes N1, N2, and N4 remain. So in this case, we can easily search the historical data. So to search this A11E67 in block I, we can follow this block, the tree nodes N1, N2, and N4. So although this approach easily achieves the provenance queries, it has too much storage overhead due to the node duplication. We can see that N1 and N1 prime, N2 and N2 prime, N4 and N4 prime share a similar node structure, but they have different hash values due to the different leaf values of V3 and V3 prime. So in this case, most of the storage overhead comes from the index nodes rather than the underlying data. So therefore, we want to design a blockchain index with less storage size and support both of the data integrity and also the provenance queries. Recently, a novel indexing technique called the learned index has emerged and shows notably smaller index sizes and faster query speeds. So the core idea is to substitute the directing keys in each index node with a learned model. the model has a much smaller size and a faster speed for locating the data. So let's consider a key value database with a linear distribution. So the left-hand side is a traditional B+ tree with a fan-out F. So the index storage cost is O(n), and the query cost is O log n with the base of fan-out F. Conversely, we can use a very simple linear model y equals to x to accurately position the data as shown in the right-hand side figure. So the storage cost is obvious O1, and the query cost is also O1. So this example is quite an extreme case. But it indicates that the learned index can outperform the traditional indexes significantly when the model effectively learns the data. So for a more general case, we can use multiple levels as a hierarchy to learn the data. The higher level model picks the model at the next level. So with all of these advantages of the learned index, we may consider applying it to the blockchain storage. So the original learned index does not consider both the integrity and the provenance queries. So to solve this, we can naively imitate the MPT's approach. So to make it support data integrity, we can combine it with the Merkle Patricia tree, and each of the nodes will be extended with a hash value. So to support the provenance queries, we can duplicate the nodes in the update path, as in the MPT. So unfortunately, this approach cannot work very well. So our experiment shows that it results in 5 times to 31 times larger index sizes than the MPT. The major reason, there are 2 major reasons. So the first is that the learned index has a much larger node size. So the fan-out of a node is mainly dictated by the data distribution. So consider a case if a larger part of data is quite linear, they can be indexed by a single model. So in this case, the fan-out can be as the same magnitude as the database size. Moreover, each of the nodes stores a fan-out number of hashes, so both for the leaf node and also for the index for the internal node. And this can make the node size very large. Second, according to the characteristic of the Merkle Patricia tree, so a 1 hash update in the leaf value in the leaf node will result in a log number of duplicated nodes. So this will further deteriorate the storage overhead. So to tackle the previously mentioned problems, we propose COLI, the column-based learned storage for blockchain. It avoids the cumbersome node duplication. So each of the state is treated as a database column, and each of the column contains the state's historical versions and the values. So to search them effectively, we store them in a contiguous manner. So since these data are sorted, so it is quite easy to use the learned models to index them and to search them. So with the column-based design, the provenance queries no longer traverse the previous blocks, but utilize the index in the most recent block. As we mentioned earlier in COLI, different versions of the states are stored contiguously. So in this case, the in-place updates may incur high disk overhead, since some of the states should be moved to make place for the new insertions. So to tackle this, we adopt an LSM tree-based maintenance approach to manage the data writes. As shown in this figure, there are multiple levels, the in-memory level and other disk levels. So for the in-memory level, we use a highly dynamic Merkle B+ tree structure to index the newly inserted data. So once it reaches the capacity, it will be flushed to the disk. And each disk level contains multiple disk runs, as in the traditional LSM tree. So when they reach the capacity, they will be merged to the next level. Each of the run includes 3 types of files. So the first is the value file. It mainly stores the blockchain states. And the second is the index file. It records the learned models. And the Merkle file hosts the Merkle tree of the corresponding run. So more detail of the index file and Merkle file will be given later. So we also maintain a root hash list for each level to compute the index root. which will be stored in the blockchain header. So now let's see the learned models we use in Coley. So we use a epsilon-bounded piecewise linear model because it is very simple but effective to be used. So first, it is a linear model, which can be formalized as the y equals slope times x plus the intercept. We also store the minimum key that is covered by the model, and this will be used in a hierarchical model setting, which will be discussed later. So the epsilon bound means that the prediction error is strictly bounded by the set epsilon. So with this feature, when we set the epsilon according to the page capacity, so we can have an optimized I/O during the data race. So in this example, when we search KQ, the model will predict to access this page PI. And we then read the first and last key in PI. If the KQ is smaller than the first key in PI, so we then access the previous page PI minus 1. So if KQ is larger than the largest key in PI, we then access the next page, PI plus 1. Otherwise, we simply search this page PI. So intuitively, we have a two-page I/O in this case. So then let's come to the model learning part. So the epsilon-bound piecewise linear model can be easily learned in a streaming fashion. We see each input key and their position in the file as a data point, and we draw the two axes. One is the key axis, another one is the position axis. So we use the special parallelogram covering all of the points convex halls to determine the model responded error. Note that the two sides of the parallelogram are aligned to the position axis. So in this case, if the height of the parallelogram is smaller than 2 epsilon, it means that the existing points can fit into a single model. And then we can try to insert the next point. So for the case of insertion S4, it satisfies the height condition in this case. But for S5, its insertion does not satisfy the height condition. So the slope and intercept of the central line in the previous parallelogram will be used to build a model, and S5 will start a new round. So in the real scenarios, there can be a series of models generated after scanning all of the states. So to index the multiple models, we build multiple layers of models. So the upper layer models are learned using the lower layers key, the K minus we mentioned before, and their position in the file. And finally, we store the different layers of models will be written to the index file. So now let's talk about the Merkle file. So in Coley, we use an M-array complete Merkle tree to ensure the data integrity due to its simplicity and the fixed structure when given the number of states n and the fanout m. So we can see that for the leaf node layer, we have n hash values, and for each upper layer, the number of hash values decreases m times. So the right part shows the layout of the Merkle file after we constructed the Merkle tree. So to construct it in an efficient way, we propose a streaming algorithm. So we maintain the Merkle tree's height number of buffers to store the temporary computed hash values. In this example, we can first compute the H3 and H4. Then we can see this buffer contains m hash values, so it is full. And then we can compute the derived hash H34 and then flush this H3 and H4 to the file. And then this will work also for the buffer C1 and also C2. So for the read operations, the get query will return the latest value of the search address. So we use a very special key containing the maximum integer as the version number, and then traverse the state with the largest key, satisfying this condition. For each run in RSM tree, we can use the models in the index file to predict the page in the value file. Then we can use the previously mentioned approach to locate the data. So for the overall procedure of the GET query, we search the LSM tree in a top-down fashion. For the, we first search the in-memory level Merkle B plus tree, and then we can search the disk levels. So the runs in the disk levels will be searched according to their freshness. So the newer runs will be searched first. And then if we have already found a result, we can early stop it. So another read operation is the provenance query. It is seen as a range query plus the generation of Merkle proof for the integrity guarantee. And we use these two special keys to search the range. And similar to the GET query, we search level by level from top to bottom. And then we can combine the partial results and proofs in each of the level. And with the Merkle hash tree, the proof consists of the sibling hash values of the search path. So the client can easily reconstruct this root hash to verify the result integrity. So another problem of LSM tree is that the level merge will incur the long tail latency, so which is also known as the write stall. So as this figure shows, the throughput may drop during the level merge. So we propose a small optimization to alleviate this problem. We propose an asynchronous merge operation. We merge this operation in an asynchronous way, but consistently commit the states. And the consistency is important in the blockchain system, since all of the honest nodes should have the consistent data storage. And for the experiment evaluation, we use several baselines. And the first one is the Ethereum MPT. And the second one is a learned index called LIP. And we combine it with a node persistent Merkle hash tree. And we also use a column-based Merkle index that adopts the column-based design with traditional indexes. And it actually adopts a two-level structure. So for the upper level, it is an MPT without the node duplication strategy. And the key is the state address. And this MPT's value is the root hash of the lower index. And the lower index follows the column-based design with the Merkle B plus tree to store the state's historical values in a contiguous manner. The baseline utilizes the RocksDB as the underlying storage, while Coley uses simple files for data storage. Two workloads are used to evaluate the performance. The small bank simulates the case of account transfers. KV Store tests the read-write, read-only, and write-only workloads. So these two figures show that compared with MPT, the storage size is reduced by 94% and 93% for the two workloads, respectively. So this comes from the elimination of the cumbersome node duplication strategy. And the throughput is also improved thanks to the smaller storage size. For the asynchronous version, it is slightly worse than Coley. For the LEAP, the learn index, it has a larger size than MPT and cannot scale for larger size for this 10 to the 4 block heights. And the column-based Merkle index has the similar size to MPT, but has worse throughput due to the refreshing of the Merkle hashes of the nodes in the update path. So the latter figure shows that with more writes, the MPT degrees more than Coley and Coley star, which indicates the better performance, the write performance of Coley and Coley star. And we also evaluated the tail latency from the right figures. We can see that the Coley star decreases the tail latency by 1 to 2 orders. And for the provenance queries, the MPT's CPU time and the proof size grow linearly with the searched block height range, while Coley and Coley star grow sublinearly. This is because Coley only uses the index in the most recent block to search the historical data, but MPT should scan the index nodes in the blocks between the queried block heights. In summary, we designed Colli, an efficient column-based learner storage for blockchain systems. We developed a disk-optimized learn index to facilitate efficient data retrieval. And the experiments demonstrate that Colli significantly outperforms MPT and other baselines in terms of both storage size and throughput. Thank you.